Have you ever copied and pasted the same Excel formula 40 times? Or clicked through the same 5 folders just to rename a set of files? There's a better way, and it starts with code. Hi, I'm Megan Puglia, and this is Unhidden Curriculum. In this episode, we're diving into the world of research coding, what it is, why it matters, and how to even get started if you've never coded before. We'll talk about the logic behind code, the lingo you need to know, where to learn, and how even basic scripts can save you hours of work and make your science more reproducible. Let's get into it. Let's start with the basics. What is code? Coding, also called scripting, is a set of instructions you write to automate tasks. Think data cleaning, statistical analysis, formatting figures, or batch renaming files. If you've done it once and you'll do it again, a script can probably do it for you. Coding can replace repetitive clicking, improve consistency, and help you keep a reproducible trail of everything you've done. Why does that matter? Well, it saves time, it reduces human error, and it makes your work reproducible and helps you scale from 5 subjects to 500. In research, code isn't about becoming a software engineer. It's about making your research life easier and more robust. Now let's go through some key terms. These apply across most languages, whether using Python, R, MATLAB, or something else. A variable is a named container that stores information. For example, you can define a variable named age and assign it the value 23. Every variable has a type, the kind of information it holds. Some common ones include integers, which are whole numbers like 12 or -3. Floats or doubles in some languages are numbers with decimal points, like 3.14. Booleans are logical values, true or false. Strings are text that are enclosed in quotes and will be read and treated like words. For example, female. You can also have an undefined variable, and each language handles this differently. In Python, it's none, in R, NA, and in MATLAB, NaN for not a number. You don't need to memorize all these different types now, just know that they exist and different types behave differently. Being able to identify and convert data types is key. Some languages will automatically coerce data types, for example, treating the number 3 in quotes as the number 3, while others won't. And that can cause bugs, like if you try to do math with a variable that holds the string value of 3 instead of the numeric value 3. Lists, arrays, and vectors are all examples of collections, structures that store multiple values in a single object. A list is an ordered collection, meaning that the values are stored in a specific sequence, and that order matters. Lists can typically contain elements of different data types, like the string male, the number 42, and the Boolean true. A vector is a one-dimensional collection. Think a single row or a single column, where all the values are of the same data type. For example, 1, 2, 3 is a numeric vector, while yes, no, maybe is a string vector. An array is a multi-dimensional collection, often organized like a grid. Think an Excel spreadsheet with rows and columns. Arrays are usually used for numerical or matrix-style data, and most languages require all elements to be of the same data type. Understanding how these collections behave is fundamental for data wrangling and analysis. There are 2 key things to know. First, what data types they allow. Again, some languages are flexible and allow you to mix data types within a collection, like having male, 42, and Boolean true all in one list. Others are more strict and require that all the elements be of the same data type, such as all numbers or all strings. Some have even stricter rules, like only allowing strings of the same length or character limit. Next, it's important to understand indexing. Every item in a collection has a location or index, its position in the structure. For example, what is the second value in a list, or which index contains the value 55? But there's a catch. Some languages, like Python or JavaScript, use zero-based indexing, which means counting starts at 0. So the first item is at index 0, the second is at index 1, and so on. Other languages, like R or MATLAB, use one-based indexing, where counting starts at 1. Why does this matter? because off by one errors, like asking for the first item but getting the second, are among the most common bugs in coding. Next up are functions. A function is a reusable block of code that does something. For example, the round function will round your number to a specific number of decimal places. Functions have a name, like round, take arguments, the inputs you pass into the function, so for example, 3.14159 and 2, and return a value which is the output from a function, like 3.14. You can use built-in functions that come with the programming language, import additional ones from external packages or libraries, or even write your own custom functions. Finally, we've got operators. These let you perform actions on variables and values. There are a few major categories to know. Arithmetic operators perform basic math, such as addition, subtraction, multiplication, and division. Comparison operators compare values. Think equal to, greater than, less than or equal to, and return a Boolean, true or false. Logical operators help you combine conditions. And means both conditions must be true, or means at least one condition must be true, and not means the conditions must not be true. These are especially useful when writing rules or filters. And operators are the building blocks of expressions, which are combinations of variables, values, and operators that can be evaluated to produce a result. For example, the expression age greater than or equal to 18 evaluates to true if the value stored in the age variable is greater than 18. Now here's the thing. All of the above only works if you follow the syntax. This is the grammar rules of a programming language. Just like spoken language has punctuation and word order, code has rules about things like how to assign variables and how to write blocks of code. And these syntax rules are slightly different across different languages. And here's an important secret. Computers are pretty dumb. They can't use context clues to guess what you meant. One missing parentheses or a quotation mark will throw an error. That doesn't mean you're bad at coding, it just means the interpreter couldn't understand the sentence. Coding is like learning to write a recipe in a new language. Get the syntax right and your computer can follow the instructions exactly. Now that we've covered the basics of vocabulary and grammar of programming, let's look at how to combine these pieces into full instructions. Programming isn't just about writing steps. It's about controlling how and when those steps happen. That's where control structures come in. They allow your code to make decisions, repeat actions, or follow different paths depending on the conditions you set. Control structures typically consist of two parts. Conditions, this is questions your code asks, like, is this true? And code blocks, these are the actions your program will take if the condition is met. There are three key control structures to know. First up is if statements. These run a block of code only if a condition is true. In this example, the program checks whether age is greater than 18. If it is, it runs the print adult command. If not, it skips it. You can expand if statements with else statements, which will run if the condition is not true. So if age is not greater than 18, rather than printing adult, the program will print child. There's also else if statements, which will check additional conditions. Like if the age is not greater than 18, but is greater than 12, it will print adolescent. Otherwise, it will print child. Next up is for loops. For loops let you repeat code for each item in the sequence. Think a list, vector, or range of numbers. They're great when you know how many times something should run. For loops use a placeholder variable like I, which stands for iteration. It temporarily holds each item in the sequence, starting with the first, then the second, and so on, until the loop has gone through all of them. For example, a Python for loop might say, for I in the sequence of 1 to 10, print I. The loop runs 10 times with I taking on the values 0 through 9. This is zero-based indexing in action. Finally, there's while loops. While loops also repeat code, but instead of looping over a predefined sequence, they keep going as long as the condition remains true. For example, if you have a variable x equals 1, while the condition x is less than or equal to 10 is true, the script will execute the function of adding 1 to x. Once x is greater than 10, this condition will no longer be met, and the block of code within the while loop will no longer be executed. Now beware of a common beginner mistake, forgetting to change the value inside the loop. That can cause infinite loops where the condition is always true and the code never stops running. Control structures make your code dynamic and responsive, and they can be combined in powerful ways. For example, you can write a for loop to run over a set of variables, and within the code block can use if statements to check if a condition is met for that particular variable. Even without writing actual code, you can start with pseudocode. This is a rough outline of your logic in plain language. It helps you map out what you want your program to do without worrying about syntax. For example, for each file in my directory, see if it has at least 10 lines. If yes, move it to a different directory. If not, add more information to the file before moving it. Then you can translate that into real code once the logic is clear. Now that you understand the basics of programming, let's talk about how to actually run your code. Most of the time, you'll write code in a script. This is a text file containing commands or functions written in a programming language. You can save and run this file repeatedly, which is one of the biggest benefits of coding: automation and scalability. Once it works every time. But how do you run that script? Welcome to the command line. The command line, also known as a terminal or shell, is a text-based interface where you type instructions instead of clicking with your mouse. Think of it as direct communication with your computer. It's like talking to the operating system in its native language. While it may look intimidating at first, just a blank screen with a blinking cursor, it's a powerful tool that gives you more precision, control, and efficiency than a graphical interface. That's the point-and-click environment you're used to, like Finder on Mac or File Explorer on Windows. You can use the command line to run your scripts, move, copy, or delete files, create folders and directories, navigate your file system, install and update software, access remote servers, or work in environments without a mouse or desktop, like research servers, high-performance computing clusters, or cloud instances. In research programming and data science, interfacing with the command line is an essential skill. The good news, once you know the basics and understand the logic behind programming, switching languages is easier than you think. Yes, the syntax differs, but the thinking stays the same. Start with the language your lab or field uses most. You can always add more on later. Here are some good languages to know. Python is a general-purpose language that's beginner-friendly with tons of libraries for data science, machine learning, neuroscience, and more. R is great for statistics, plotting, and data wrangling. It's widely used in psychology, epidemiology, and academic research. MATLAB is common in neuroscience, engineering, and signal processing. There's strong support for matrix operations and visualization. Bash is a scripting language used in the command line for automating tasks, managing files, and chaining programs together. JavaScript is used to build interactive websites and dashboards. It's helpful if you want to share your data or visualizations online. And SQL, this one's not a full programming language, but it's essential for querying and managing data stored in relational databases. Finally, Julia is a newer language designed for high-performance numerical computing. It's great for simulations, modeling, and large-scale analysis. Here are some platforms and tools you might use as you start coding and collaborating in research. Text editors, or IDEs, integrated development environments, are where you write and run your code. Think of them like Microsoft Word, but for programming. IDEs often include helpful features like syntax highlighting, auto-completion, and built-in terminals. Some examples include VS or Visual Studio Code, which is multi-language and highly customizable, RStudio for R, and Jupyter Notebooks, which is great for combining code and commentary, especially in Python. Repositories are online storage systems where your code lives. Repositories let you track changes over time, called version control, back up your work, and collaborate with others. Examples are GitHub and GitLab. Package managers help you install and manage external packages, which are bundles of code written by others to extend your programming language's functionality, like new stats functions or data visualization tools. Some examples are CRAN for R and pip or Conda for Python. Project platforms help you manage and share entire research projects, including datasets, code, preprints, and documentation. They're often used in open science and team-based research. Some common examples are the Open Science Framework, or OSF, BrainLife, which is specialized for neuroimaging workflows, or NeuroDesk, a portable neuroimaging environment. These tools help you write, run, share, and organize your code. Good tools are only part of writing good code. Just as important is how you communicate your code's purpose and manage its evolution over time. Comments are notes written for humans and ignored by the computer. Use them to describe what your code does and why you did it that way. Well-commented code is a gift to your collaborators and your future self. Version control means tracking changes in your code over time. It helps you go back if something breaks, collaborate with others, and avoid overwriting important files. Git is the most common version control system and will be a topic for a future episode. GitHub is where you can host your code online. Even if you don't use Git yet, start simple. Save versions with descriptive file names with date in the format of year, month, day for easy sorting. Writing clean, well-documented code and managing versions is just the start. Coding is a skill you build over time, and everyone hits roadblocks. Even the most experienced programmers face errors all the time. The key is knowing how to approach them calmly and systematically. So what should you do when you get an error? Start by reading the error message carefully. It usually points to the problem and where it occurred. Know common errors to check for, things like missing punctuation, syntax errors, data type mismatches, off by one indexing mistakes, or infinite loops where conditions never become false. Start small. Isolate the problematic section by inserting print or debug statements to check where your code breaks. And finally, try what I call onioning. Peel back each part of the line causing issues, checking variable names, values, and function calls step by step. If you still need help, these communities and tools are invaluable. Stack Overflow. Google your error message in programming language, and likely someone has already asked your exact question. If not, feel free to post it in this forum. GitHub issues. Look for similar problems reported by other users. Reddit. There are great Substacks for learning and debugging code. Try Learn Programming, R Language, or Data Science. YouTube has so many helpful videos with step-by-step guides and courses. ChatGPT. Be careful with this one. It does a decent job explaining code, but I haven't been impressed by its ability to write code yet. Always verify the output. Lastly, turn to your lab or team. Remember, everyone starts somewhere, so don't hesitate to ask for help. And here are some other super helpful courses, tutorials, books, and practice sites to check out. Coding is about more than lines of text. It's about building workflows that are reproducible, scalable, and far less error-prone. If you're just getting started, don't try to learn everything at once. Pick a project, write your first script, try your first loop. In future episodes, we'll take a deeper dive into each specific language and walk through examples step by step. But until then, keep your data tidy, your scripts commented, and of course, stay curious.